anyone that works with centrifugal pumps is always concerned about NPSH, and it seems to be the demon that all process engineers have to deal with. Anytime we have a centrifugal pump, the big question is, do we have enough NPSH to keep the pump happy? So what we're going to look at today is how can we determine what the NPSH requirements are for the pump before we go talk to vendors, and can we make decisions about the NPSH can we make decisions about pump design that will impact the NPSH, and what does that tell us about other aspects of pump operation? That's what we're going to look at. So I'm Kevin, and so we're going to explore centrifugal pumps and NPSH. Okay, so first, a little bit of a refresher. In a previous video, I looked at a number called the specific speed, and how this can tell us something about pump efficiency. So specific speed is NS, and that is simply, it's a kind of a dimensionless number. It is the RPM, or the speed of the pump in RPM, the flow rate in US gallons per minute, and the pump head, the square root of the flow rate, and the pump head to the 3/4 power in feet. Okay, and so this number is a parameter that tells us the shape of the pump, or pardon me, the shape of the impeller. A low specific speed impeller is very radial. It looks like the disc brake on a car. Okay, so conversely, a high specific speed impeller is more like a propeller. That's all I can say. It looks more like a propeller. So that number tells us what the impeller is. Yes, so the specific speed tells us about the impeller design. Okay, but we don't want to know that. We want to know something about NPSH, because this doesn't tell us. Okay, so what can we know? What can we find out? Well, it turns out if we just replace H with NPSH and take that to the 3/4 power, that is called the suction specific speed. And this dimensionless parameter was first developed by, I think it was Igor Karasik, sometime in the 1930s, and he found this to be a pretty reliable way of estimating the NPSH required for a pump under different conditions of speed and flow rate. And the thing that dictates suction-specific speed is the size, or is the diameter of the suction inlet, or the suction eye. That's the thing that tells us the suction-specific speed. So if the inlet to the impeller, the suction eye, is pretty narrow, if it's a small diameter inlet, it has a low suction-specific speed. If there's a large diameter inlet to the impeller, so if it's like that big around, this has a high suction-specific speed. So suction-specific speed is a geometric number that tells us something about the suction to the impeller casing and the impeller eye. Now, suction-specific speed is important because it also highlights the issues of recirculation instabilities. It turns out that low suction-specific speed pumps are very resistant to instabilities caused by recirculation. Pumps with a high suction-specific speed are very susceptible to instabilities caused by recirculation. So we still haven't answered our question. The question was, what can we do about NPSH? If we always want a low NPSH, the math says always go with a high suction-specific speed pump. So what's the trade-off? Turns out there's a trade-off. That's over here. The trade-off is all about reliability, and this was sorted out back in the 1970s. So if we look at a graph of suction-specific speed on the y-axis and percent of best efficiency point flow rate, or design flow rate, on the x-axis, there's an operating window here around the best efficiency point, or the perfect flow rate point, where the pump operates really reliably. If we operate at a flow rate less than that, the pump's not too happy. It still works. but we can probably expect some reliability issues. The first things to go will be the bearings and the seals. Okay, and then if we go to a really low flow rate, it just dies. Okay, we're going to kill it. Now, as we increase suction-specific speed, this operating window for the range of flow rates where this pump is happy, that operating range goes down. So if the pump has a nice wide operating range with a suction-specific speed of 7,500, that's where I like to specify pumps. If we go up to, say, 11,000, it's at a point where the operating range is considerably narrower, and we have to pay very close attention to make sure that pump always operates close to the best efficiency point. Because if it strays too far outside that, we get those recirculation instabilities, and then we'll start to do damage. So we'll damage the seals and we'll damage the bearings. Not to say that you can't operate with a high suction-specific speed pump. We have to be careful. So if you want a low NPSH pump, go with that. You need to select a high suction specific speed, and the trade-off is about reliability. And we have to keep that in mind. So make sure the flow rate is close to the best efficiency point, and also make sure that this inlet line is long and straight and doesn't have any bends in it that causes swirling and recirculation, to make sure that that impeller has the best chance of good performance. So that's it. Happy pumping. Take care. Bye-bye.